The last talk of the session is by Pjanka on numerical simulations of internal shocks in microquasar. Go ahead.
Thank you. So my name is Pjanka, and before we break for coffee, I would like to say a few words about simulations of internal shocks in microquasars. So this is a project that I'm doing with Camilla Demidem and Alexandra Viledina from Nordita in Stockholm. And we are still pretty early in the physical part of the project. We were actually mostly working on technical things so far. So this talk will be a bit of a mix between a literature review and some early results and presentation in preparation for the main part of the project. But with that, let's start with some motivation. So why do we need an internal shock model in the first place? Before in this conference, and I'm sure everyone here might know that jet spectra in hard states of X-ray binaries are typically flat. So here on the left, we have a Cygnus X1 spectrum from Zdziarski-Lubiński-Sikora in 2012. And in the circle, we have the jet spectrum. This is an EFE versus photon energy plot. So the slope of 1 means that we have a constant slope independent of photon energy. And the way this is typically modeled is with the classical model of Bluntford and Kinigal, which means that we assume that we have a conical jet with a constant bulk Lorentz factor. We assume the magnetic flux to be constant, and importantly, we assume the energy distribution of the emitting particles, or electrons in this case, to be constant. And this last thing is pretty difficult, actually, because those electrons will be, first of all, radiating away some of their energy. And secondly, or perhaps more importantly, they will be adiabatically expanding into the medium of the jet. And they will be losing the energy. So we need some kind of a mechanism to replenish this lost energy. And there are a couple of ways to do that. So first of all, we have already heard at this conference, and it would be pretty unexpected for the jets to be exactly conical. So they are probably a bit of a different shape. And there are ways in which just by changing geometry of the jet, you could get away with those energy losses and still have the flat spectrum and the radio of the jet emission. However, it is generally expected that this would require some fine tuning of the shape of the jet. So it seems quite unlikely to be the solution here. The second possibility is that we can have magnetic reconnection within the jet. So we can transfer some of the magnetic flux, some of the magnetic energy carried by the jet into particles and reheat them as they travel down the jet. So there is a whole community with many successes working on this. However, there is an alternative, and I will talk about this here, which is the internal shock scenario. So in this case, we take into account that the jet is actually unlikely to be a sort of a laminar flow with a constant Lorentz factor. And instead, we assume that there is some variability in the ejection Lorentz factor. So we generate parcels of gas that will move at different speeds, and then eventually they will collide somewhere up the jet, produce internal shocks, and those internal shocks would hopefully accelerate particles. In the model, this is usually modeled with discrete parcels of gas moving up the jet, which then collide and accelerate particles. It has already been mentioned that there are some troubles with this model, but what I would like to point out that it is actually, it has some successes as well, and I find them quite impressive. I will probably only have time to just flash this slide in front of you. But the important part is that if you feed this internal shock scenario and produce an emission model, and you feed the power density spectra of the X-ray emission, you can actually do quite beautiful predictions of what the spectrum and even some timing properties of X-ray binaries look like. So here are some references. As I said, I don't really have time, I think, to go through all of this, but we can see this beautiful spectral fits. And this is not really a fit. So this is just a prediction from the X-ray power density spectra. from Polt et al. In 2018 here for different phases of the outburst. We have some timing data, and there are some caveats here, but for instance, the time lags are predicted from the X-ray quite impressively, in my opinion. However, here I would like us to go a bit under the hood of the model. And as I mentioned, all those models that are predicting emission from the internal shock model assume that we just inject those shells with some distribution of Lorentz factors. Then those shells will collide with some prescription of what happens then. They produce internal shocks. And most of those models will then use some kind of a prescription to how those internal shocks will then accelerate particles. Now there's a problem here because it has been found that it is actually pretty difficult to accelerate particles in either magnetized, perpendicularly magnetized, or relativistic shocks. And the reason for that is in diffusive shock acceleration, we need the particle to be able to move across the shock front, back and forth, gaining energy. And this is the way we would accelerate particles. But if we do have some magnetic field with field lines parallel to the shock front, then particles with low energy and a small Larmor radius will just stay fixed with the magnetic field line, and they won't be able to cross the shock repeatedly, so they won't accelerate, or at least it will be very difficult. Similar problem exists for relativistic shocks, where we obviously have the speed of light limit, so it's actually pretty inefficient for the particle to keep crossing the shock, since it can move away fast enough that it just can't go back. A solution has been found recently by some authors that shock corrugation or rippling of the shock front can help reduce those problems. And this is done by two different mechanisms, which is visualized quite beautifully here by the PIC simulations of Ligorini et al. In 2021. So what you see here on the right, the colors are generally magnetic field. And we have some particle tracks, and I guess the easiest to focus your attention on is the red one. And now the first mechanism occurs actually in front of the shock. So here we have a shock front, so we can see the ripples in the shock. And those ripples will actually launch electromagnetic waves into the pre-shock medium. Those electromagnetic waves can then interact resonantly through say, Wakefield acceleration with the particles, and they will preheat those particles even before they actually reach the shock front. So this is one thing that is important. And the other thing is that behind the shock, which we see here at the top, those ripples will produce turbulence, in this case, two-dimensional turbulence. Those are PIC simulations. Those preheated particles can then interact with the structures of the turbulence in a manner similar to second-order Fermi acceleration. And this way they can accelerate to quite significant Lorentz factors, about 100, at least in this case. So corrugation helps, and clearly it seems to be important, or at least that's the question, whether it is important. So the thing we would like to ask here is how, if at all, it changes the results of the internal shock model. So the idea for our project is to essentially produce such a shell collision on macro scales, but with appropriate tracing of the particle acceleration. And the way we would like to do that is by borrowing an idea from cosmology simulations and do a sort of zoom-in simulation. So obviously what we would like to do is have a PIC simulation of the size of the jet that would then just accelerate particles and produce the spectra. But unfortunately, unless you're willing to wait about 50 years with computational power, I guess we won't be able to deliver that. But what we can do is we can start at essentially the scales of the skin depth of the particles in question at PIC scales. And my colleague Camilla Demidem will be doing those simulations. And here we can have a rippled shock and then simulate accurately acceleration using those two mechanisms. Then once the particles accelerate enough, we can take the most energetic particles, the ones with the largest Larmor scale, almost at the size of the box. And we can sort of zoom out move our schemes to MHD and just inject those energetic particles as test particles that only interact through magnetic fields. Then we can run the MHD simulation, track the particle acceleration there, and we can repeat this since we have now higher energy particles. We can move those into larger scales, accelerate them again in MHD, and keep going until we reach the macro scales. After all that, we can just rescale everything and get the particle energy distribution and the synchrotron spectrum that we get from that. So this is the general idea. You can probably appreciate that there's a lot of moving parts here. So with a lot of moving parts, especially in simulations, it's a good idea to make sure you understand every step before you go into it. And what we have done so far, we did a lot of work on the technical side of it. So for instance, the test particles and so forth. But the first physical thing we would like to check is how those rippled shocks actually behave just in MHD. So we did this simple setup here. And let's just focus on this diagram in the interest of time. We have two relatively dense magnetized shells with typical parameters for X-ray binaries, at least for those regions. Those are surrounded by ambient, non-magnetized, low density field gas, and then inside them there are two cases. So one, we just fill it up with ambient gas, so we have a 1D simulation like the ones that has been used before, and the other one we introduce those density ridges that will cause the shock to ripple to see the difference essentially between those two cases. Now maybe I do have time to show just one movie. So this is one of the first cases, and this is just the difference between this 1D case, which we can see in density here at the top, and this corrugated case in density here. So those are the ridges that I told you about. I guess the plot I would really like you to focus on is this one. So that's the light curve and synchrotron with sort of typical assumptions that are done in those studies. The blue curve is the corrugated case and the black curve is the non-corrugated. So we already see that there is actually a difference, which did not have to be the case. We might as well have gotten the same thing. So this is the first case. Another interesting thing is that if we go to wider shells, so the only thing I've changed here is just the width of the shell, everything else is the same. The effect is actually opposite. So now the non-corrugated shape is brighter. So we are working on this. Of course, there's a whole parameter study that we want to do before we go into particles. But really the point of this talk is to ask you guys for input, since we can go in many directions here. There's a lot of parameter space. So what would be most useful for us to study in this project? And with that, I end, and thank you very much.
Thank you. So is there input? Pop has input.
Hopefully.
And perhaps a microphone.
Pierre-Olivier speaking, so very nice talk. So if I understand your procedure, you start for the small scale, then you take the particles and you integrate in larger scale boxes. Yes. But don't you expect to have also the reverse impact of what occur on large scales that can change what you have in the small scale boxes?
Yes, I suppose that is a possibility if we have large enough energy losses, but I would expect that in this case acceleration would be
or a change of the magnetic structure. I don't know, for any reason. Mm-hmm. I don't know.
I think if we are careful to just stick to the shock itself, the particles that pass it won't have time to cool enough to change the low energy distribution. As we've seen those mechanisms that help with acceleration here, the particles are just moving through the shock anyway, so they don't do this sort of diffusive shock acceleration that we're used to, where they just stay at the shock front. So if we accelerate them, they will obviously cool down the line, but hopefully this will be outside our box.
Andre has another question, and then online Greg after Andre.
Thanks for this nice talk. We know that in many cases, the first collision would occur above 1000 RG, right? Because of the time lags of the optical versus phase space. And how you explain this feature in this model?
Yes, so I guess this would be a great question to Julien Mazzac's group and the people who actually work on those global models. In this particular case, I can only refer you to the paper, since I'm sort of working on the, it's macro scale on the plasma physics side, but it's still micro scale collision on the actual jet. So yes, I'm not, I don't think I'm the expert to ask here, but that is a good point.
Okay, last question, Greg, please.
So I realize that there are, as you mentioned, a lot of potential knobs to turn, but do you guys think that there might be a way to basically simplify the calculations in some way in terms of the results that you're getting to like libraries of how the shock's moving through or something along those lines? And that's something maybe even eventually us poor observers could use.
Yes, so that I guess that would be the ultimate goal. So what we really would like to have in the end is just some simple model, one-line equation that we can just incorporate in those global internal shock models. Essentially, some form of a correction that we can do to that. So that is our goal in the end. To if we do see a difference, how we can parameterize this difference, not even as a library, but it's just dependence on the parameters that we can then educate in an educated way, guess for those parameters. So it is the goal. At this point, we are still pretty early, so I'm not able to tell you whether this will be easy or doable, but I certainly agree that this is the way to go.
Thank you.
Okay, let's thank the speaker again, please.